All right. So we left off with question 10, which is another Newman projection problem. So it says draw a Newman projection for the following compound viewed down this carbon-carbon bond. So let's try again. This time I'm not going to use my green and blue pen. We'll just start with the carbon in the front. Oh, I said I wasn't going to. Start with the carbon in the front. Then we have the carbon in the back. All right, so going straight down, we have this methyl group. So we'll pencil that in. Then we've got something going up and to the left and something else going up and to the right. Could anybody tell me the chlorine, would it be on the left or the right? This one. The chlorine be on the left or the right? Absolutely. Yes, my chlorine is on the left, and so the hydrogen is on the right, right? There's a hydrogen that isn't drawn. And then going straight up in the back, I have the chlorine, which is in the plane of the screen. Then I have something going down into the left and something going down into the right. So which side would the bromine be on? Would it be on the left or the right? Bromine atom, not the methyl group. Yeah, absolutely. So I have a bromine here, and I have the methyl group. There you go. All right, something that we're going to see much later on is that you're going to have to be able to take Newman projections and rotate the bonds. That's not something we see until I think it's chapter 7 or 8. 7, 8, something like that. So just to put the bug in your ear, Newman projections don't go away. All right, let's try this one here. We'll go a little faster this time. Here's the eyeball, right? We're looking down this carbon-carbon bond. So we've got the carbon in front. We have the carbon in back. The carbon in front, we have an ethyl group going straight up, right? This is CH2, CH3. So we have an ethyl group. I'm just going to put ET like this. So ET, that stands for ethyl. And same thing, ME, in case you probably haven't figured it out, that stands for methyl. So we have an ethyl group. Then we have something going down into the right. We have something going down into the left. So there's a methyl group, and the methyl group is going to the left, right? That's this methyl group right here. Then there's a proton that's not shown. That's going to be over here. Going straight down, I have another ethyl group. So there's another ethyl group. I'll put that here. I have something going up and to the left and up and to the right. Let's see here. So the methyl group, the second methyl group here, the one in the back, is that going to be pointing to the left or the right? Could anybody help me out with that? Yeah, absolutely. It's going to be pointing to the right. So I'll put methyl group here, and then I have a hydrogen here, which isn't shown, right? There's a hydrogen that's left out because this is a bond line structure. Okay, let's take a look at this one. It says draw the lowest energy conformer of the following compound as a Newman projection. So you have to know a little bit about nomenclature to know what the carbon 2, carbon 3 bond is. 1, 2, 3, 4. This compound is 2-methyl butane. And so what we're going to do is we're going to look down. God, I cannot get a yo this morning. All right. Here we go. Let me just... All right, so let's see here. 2-methyl butane, we want to look down the carbon 2, 3 bond, and we want to give the lowest energy conformer. So if you're not sure what the lowest energy conformer is, I'm sure you can draw the Newman projection though. So we're going to have 2 methyl groups. So we have 2 methyl groups, and we also have a proton. So we'll put the proton here. All right, and then in the back, we're going to have a methyl group. Remember, it doesn't give us any kind of dashes or wedges or anything like that. So what I'm going to do is I'm going to put the methyl group over here. It doesn't matter where it is. Okay, I'm just trying to draw a Newman projection because I've got 2 protons here. I'll put 1 here and I'll put 1 here. However, this is not the lowest energy conformer, is it? Right? How do I know that? Because I have a gauche interaction here. And so is there a way for me to eliminate any kind of gauche interaction? I guess there isn't a way to eliminate any gauche interaction in this compound, is there? Now that I look at it very closely. So in fact, this would be the lowest energy conformer that we have, right? It wouldn't matter. Like, let's say if you said, Well, I'm going to rotate the bond. I'm going to rotate this bond, and I'm going to put this methyl group up here. I'm going to move it up here. Well, you're still going to have a gauche interaction here. And so this would be the lowest energy conformer of this molecule, right? A staggered conformation. If it was eclipsed, that would definitely be higher in energy. Okay, let's move on to the next one. We have a cyclohexane chair that somebody drew here. It's not the greatest chair in the world, which is funny since it came from a drawing program. But anyhow, it asks us to draw in all axial hydrogens. Okay, so remember that when you have two bonds that are pointing up, right, like this, you see both of these are on an upward trajectory. That means that your hydrogen is going to be going straight up like this. Same thing here. We have a bond going this way and a bond going up this way. So in this hydrogen, it's going to be going straight up. And you should remember that axial positions alternate. So it goes axial, equatorial, axial, equatorial. And then this one would be axial, right? So we know that on this bond or on this carbon, we should have a hydrogen pointing up. The same thing applies for the hydrogens that are axial pointing down. There's three of them, right? If we have a bond going down this way and one going down this way, that means we have a hydrogen atom going straight down like this. We keep alternating. We're going to have a hydrogen in the back going straight down like this. And then we have one on this carbon going straight down like that. All right. Give me a thumbs up if you're with me on the axial hydrogens. I'm sure everybody's been practicing their axial and equatorial. Great, right? And if you're a real keener and you said, I'm going to draw in all the equatorials, I'll draw them in quickly in green, right? So this one, right, would have to be parallel with these two lines that are one bond away, right? This one would be have to be parallel with two bonds that are, this one has to be parallel, the two bonds away from it. So that would mean this one and this one. This one has to be parallel with this bond and this bond. This one has to be parallel. Really doing my best here with this bond and this bond. And I'm missing one, right? This one here would have to be parallel, supposedly, with this bond and this bond. All right, this is my best handiwork, I guess, right? And then, so we have 1, 2, 3, 4, 5, 6. We have three of them that are pointing up and three of them that are pointing down, right? So if I put a little U, this one's pointing up, this one's pointing up, and this one's pointing up. This one's going down, this one's going down, and this one's going down. So remember that axial and equatorial, they alternate, okay? And also remember that up, if we have three protons that are pointing up, then we have three that are pointing down, whether it's axial or equatorial. Anybody give me a thumbs up on their ability to draw a chair? Anybody feel good about their chair drawing skills? Because we're going to, okay, awesome, because we're going to have to draw some chairs in this one here. And I didn't go much over the kind of our textbook's way of doing things. He has a particular way of doing stuff, and I'll just show you what I mean here. So it says, draw both chair conformers of the following compound. Okay, and this can be done a variety of ways, but I'm just going to do it like this. Okay, so if I put this here, now it doesn't tell you whether the hydroxyl is pointing up or down, so that's neither here nor there. But if we have two chairs that are interconverting, then one of them it's going to be in an axial position and one of them it's going to be in an equatorial position. So kind of, I think the way he does it in the textbook is if the carbon one, if carbon one is the carbon on the top, he usually picks that as being the one on the top right-hand side, okay? So let's just put it in the axial position just for the heck of it. And if you're thinking, I put it in the equatorial position, no problem, right? But I'll just put it in the axial position like this. So then when you flip the ring, right, if this is carbon one moves down here when you rotate those bonds. So now it's still going to be pointing up. However, it's going to go from up and axial to up and equatorial like this. Give me a thumbs up if you're with me even part of the way, because obviously you still have some time to study before the quiz. Okay, so good. Thank you. Okay, now I just want to show one more thing to prove that if you started out with drawing the hydroxyl pointing down, that's not a problem. I'll prove it to you. Look, if you had done this, okay, let me erase what I wrote. If you said, oh, I'm going to put the hydroxyl pointing down, no problem. Here it's down in equatorial. Then when you flip the ring, it's going to be down in axial. And if you're wondering, aren't these two different compounds than what you just drew? No, these are the exact same compound. They're just drawn a different way. Okay, so this is where molecular models can come in handy. So with that in mind, let's try another one here. It says draw the most stable chair conformer. Draw the most stable chair conformer of the most stable isomer of 1-ethyl 3-isopropyl cyclohexane. So first, let's just draw bond line structure. So if we have an ethyl on carbon number 1, and then we have an isopropyl on carbon number 3, something like that. All right, do you guys remember that axial and equatorial alternate, right? We go axial, equatorial, okay? If things are all pointing up is what I should have said. So we have up and axial, up and equatorial, up and axial, up and equatorial. So if we imagine that this group here is up and equatorial, could anybody tell me, you know, what position would the isopropyl group be in to make it the most stable? Would it be down, or would it be up, and then would it be axial or equatorial? Can anybody answer that question? Not the easiest question in the world. So it would, okay. So if we have up and equatorial, right? Let's say you draw this proton in. Then this has to be up and, oh, I didn't put a hydrogen there. Then this group would have to be up and axial. So that means that if the isopropyl is pointing up, that means it's up and equatorial. Does that make sense to everybody? Right, the one that's the proton on here that's pointing down would have to be axial. Right, this is down and axial like that. So in fact, the most stable conformation is one where we have both of the groups in an equatorial position. So there's a number of ways you could draw this, okay? Not many ways you could draw this, but let's just draw a chair. Practice our chair drawing skills, okay? So let's start by, why don't we choose this as our first carbon, and we'll have the ethyl group pointing up, and so there's an ethyl group that's pointing up and equatorial. So then if we count 1, 2, 3 carbons, maybe I need to move this over a little bit. There we go, let's move that over here. Then I have the isopropyl group that's going to be up and equatorial. So here's my isopropyl group, and that would be the most stable conformer of this molecule, right? If you were to draw both of these pointing down, or if you flip the ring, they'd both be up, but they'd both be axial. All right, so that would be the most stable conformer of this compound. All right, let's take a look at the next one, which is in the exact same vein. It says, which compound is more stable? Let's think about this. If in compound 1, if this group is up and equatorial, right? Because we know the equatorial is more stable than axial. That would mean that the proton here that's up would be what? The next one, it goes up equatorial, up and axial, right? So this one's up and axial. And so that means that this proton that's pointing up is going to be equatorial. So that means that this group, this methyl, is going to be going down and axial, right? So that means you have one group that's axial and one group that's equatorial. All right, if we think of the next one, though, if this is up and equatorial, then this group again has to be up and axial. So that means that this group is going to be up and what? Da-da-da-da, equatorial, right? So that means that in the second one, it can exist in a conformation where both groups are equatorial. And so 2 is going to be the more stable of the 2. Give me a thumbs up if you follow me on that one. Again, this is where molecular models can come in handy, right? So if you were to draw the chair of the first one, let's see here. If we drew number 1, what's it going to look like? That's not the best chair in the world. It's actually kind of crappy. But anyhow, if we have this group is going up and equatorial, so if we count 1, 2, 3, then the next methyl group is going to be down and axial. Where's the one in blue? So let me just draw old blue here. There we go. So if we have something that's up and equatorial here, we count 1, 2, 3 carbons away, and this guy's going to be up and equatorial. So there you go. This one is going to be the most stable of the 2 of them. All right. Question number 17 is one I would expect everybody to get correct. Are the two substituents cis or trans? Could anybody answer this one for me? Are they on the same face of the molecule or opposite faces of the molecule? Are they cis or trans? Two methyl groups. So let's think about this. So this group is going down and is equatorial, right? Because you know you have a hydrogen going straight up here. And on this one, right, you have a bond going this way and a bond going this way. So we have a hydrogen that's going straight up here. And so that means that this group is also down and equatorial, right? It's parallel with these two lines here, are pretty close to parallel. So that means they're both on the same face of the molecule, right? If you were to draw bond line structure, it would look like this. You have a methyl group going down and another methyl group going down. So they would be cis to each other. Does that make sense now that I showed you? They're on the same face of the molecule. Cha? Okay, cool. All right. There you go. Ooh, this one's always, it can sometimes be challenging for students. But this one is, I've looked at enough ACS study guides and MCAT and PCAT and all that good stuff to know that, and sorry, don't want to leave out the DAT, okay? Yeah, one of my students is in dental school, former students is in dental school right now. So they love to ask this question, okay? Can you just draw a bond line structure of this Newman projection is all they're asking, okay? So let's see here. We've got, I'm going to try to color code this or something maybe. So we've got the carbon in front. I'll do that one in red. We've got the carbon in back, okay, like this. So if I put the carbon in front in red and the carbon in back, this is not proper drawing, by the way. You're not supposed to color your carbons like this. This is for instructional purposes only, okay, just to try to help out. Okay, so this methyl group is in the plane of the screen, okay? So that means that this methyl group on the carbon in red is going to be going straight up, right? That's not on a dash or a wedge, okay? But you're kind of looking at it from this angle, right? Your eyeball, I don't know why the pupil is there, and yeah, so you're kind of looking at it from this angle. So you see that there's an ethyl group in the back, right? So it's just a matter of what's pointing in front and what's pointing in the back. So if you're taking the carbon in red and you're tilting the whole thing towards the left, then this methyl group, could anybody answer, would it be going in the page or out of the page? Would it be on a dash or a wedge? The methyl group that I have in the black circle. Would it be in a dash or a wedge? It's going to be on a dash, okay? Because, right, we took this whole thing and we turned it to the left. We took the whole structure, right? Because the carbon in red is on the left and the carbon in blue is on the right. So the methyl group that's in the black circle is going to be going into the page. All right, like that. And then the methyl group on the other carbon, on the blue carbon, is going to be coming out of the page, like so. All right, and you can practice this by looking down this bond and then trying to draw the Newman projection, right? So if you try to draw the Newman projection, let's see here, you have a dot here. So you have a methyl group going straight up. You have a methyl group that's going down here. Then you have a proton down here. Then you have the ethyl group going straight down. And you have a methyl group that's coming up on this side. And then you have a proton over here, right? And this is the exact same thing that we have. Okay, so you're going to have to practice your Newman projections. Of course, if you have any questions, don't hesitate to ask me. What's the correct stoichiometry for the balanced redox reaction? Well, if there's one thing you got to do, it's be able to balance a combustion reaction. This is a Gen Chem 1 question. Gen Chem 1. And so first what you want to do here is determine what the molecular formula of this compound is. It's a saturated hydrocarbon, so it must be C5H12, C5H12, plus O2 gives you CO2 plus water. So when you're balancing a combustion reaction, here's the order. You always do carbon first, hydrogen second, and you always, 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 100% of the time, no exceptions, save oxygen for the last. All right. So if we have 5 carbons and we only have 1 carbon in CO2, What stoichiometric coefficient do I need to put in front of my CO2? Start with that. Need to put a 5. Thanks, Eric. All right, then we have 12 hydrogens, and we have H2O. What coefficient do I need to put in front of my water molecule? A 6. Good again. All right, so then we tally up the total number of oxygens on this side. How many total oxygens are there in the products now? 16, exactly. We have 16 oxygens. So something times 2 gives me 16. That something is 8. Something is 8. And there you go. Hot dog, we have a wiener. Done. That is balancing a redox reaction for the combustion of a hydrocarbon. Pretty straightforward. So remember, carbon first, hydrogen second, and always, 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 always save oxygen for last. Okay, let's see here. Question 20. There's a few questions in the textbook like this. What's the relationship between these two compounds? Are they identical constitutional isomers or completely different? Anybody? A, B, or C? Yeah, it's C, right? These are completely different things. Why? Because they don't even have the same molecular formula. Okay, this compound is C5H12, and this is C5H10. Right, so if we have a saturated, let's just write here. If we have an alkane has a formula of CnH2n plus 2. A cycloalkane doesn't have that formula. A cycloalkane is CnH2n because you lose 2 hydrogens when you tie 2 carbons on the end together to make a ring. So these have completely different formulas. The one on the left is pentane, and this one is cyclopentane. Therefore, these two things are completely different. All right, here we go. Let's draw some ring flips. Like a house flip. This is like HGTV here. Draw some ring flips. Okay, so remember what we're going to do here is we're going to say 1, 2, 3. So when we flip the ring, right, this carbon is going to go down in that direction. So we have 1, 2, 3 now. All right, so if the tert-butyl group is going up and axial, that means that in the flip, it should be going up and equatorial, right? So we're going to draw something that looks like this. Yes, perfect. Thanks, Katana. So up and equatorial. So there's our tert-butyl group like this. And the methyl group is going up and axial. So it is going to be going up and equatorial, just like that. All right, the next one. So if we count this as carbon 1, 2, 3, 4, and we'll put 1, 2, 3, 4, like that. The chlorine is going down and equatorial, so it must be going down and axial here. Yep, good. Thanks, Hannah. Perfect. The methyl group on carbon 3 is going up and axial, so it must be we flip the ring, it's going to be up and equatorial. Perfect. We draw up and equatorial, and the last one is the chlorine, which is up and equatorial. So in here, it's got to be up and axial. All right, let's look at the next one. Just number our carbons. So we've got carbon 1, 2. That's all we need. So we have carbon 1 and 2. On the first one, the fluorine is up and axial. So on this one, it's going to be up and equatorial, like this. That's carbon 1. And on carbon 2, the hydroxyl is up and equatorial, so it's going to be up and axial here. And then the methyl group was down and axial, so it's going to be down and equatorial here. And that is carbon number 2. And there you have it. Can I ask you a question about the first one? Okay, if I call this, I'll call this A, and I'll call this B. Could anybody tell me which one of these is going to be the most stable conformation? Yeah, it's going to be B, isn't it, right? We'll put here most stable, right? Because both substituents are equatorial. Good. Sarah or anybody else, could you tell me could you name the kind of interaction that's experienced in A that contributes to its instability, or I should say higher energy, really? Could they name that interaction? Yeah, heck yeah. Thanks, Savannah. The 1,3 diaxial interaction, right? Absolutely. So here we have a proton, and here you have a methyl group and a tert-butyl group. You can imagine they're crowding each other big time, right? We call that the 1,3 diaxial interaction. Let me quiz you on something else. Let's go back here. Let's go back to a Newman for a second. There's something I wanted to ask you about that. Let's try this one here. Okay, we're in lots of room. Does anybody remember what this angle is called? This theta angle something. Does anybody remember? Well, it's 60 degrees, obviously, here. But could anybody tell me what that angle is called? Yes. Wunderbar. It's the dihedral angle. Dihedral angle. Or the torsional angle, right? Is another way of calling it. All right. I usually just call it the dihedral angle. It's what I cut my teeth with. So, okay, cool. Cool. We get some good nomenclature practice. Who wants to try doing one more beast? This is giant bicyclo compound. I just threw this on here at the end, I guess. It's not even in the problems. I don't even see it in the stuff that I had done before. So let's just do it as a group, I guess. All right. So let's see here. We've got two bridgeheads. I've got a bridgehead here. I've got a bridgehead here. Okay, so it's some kind of bicyclo. I don't know, where do you want to start? So should I start numbering at the red bridge or the blue bridge? Anybody? The red one, absolutely, right? You know, because here I have 1, 2, and I have a substituent on carbon 2. Here I have 1, 2, 2, right? Which you might fall into that trap, but remember, you're always supposed to go with the longest bridge first. And this bridge has 3 carbons in it, but this bridge only has 2 carbons in it, right? So we're going to start numbering on the red carbon. Let me just delete some of this spinach that I have here. So let's just, come on. What am I doing? There we go. So let's do something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something like that. So this is some kind of bicyclo. 3, 2, 2. 3, 2, 2. Is it 1? No, sorry, 4, 2, 2. My mistake. 4, 2, 2. Decane. All right. Yes, you always go with the longest bridge first, okay? And then after you've identified the longest bridge, right, Hannah, you would ask yourself, well, should I start numbering the way I have it, or should I go 1, 2, 3, 4, 5? Well, if you do it in red, the first substituent is at carbon 2, but if you did it in the blue way, the first substituent would be at carbon number 5. So you always go with the longest bridge first. Yeah. All right, so we have a bicyclo 4,2,2 decane. We have 3 substituents. It's 2,7,7. We have 2,7,7 trimethyl bicyclo 4,2,2 decane, and that's the whole thing. All right, there we go. So we've solved every single one of those practice problems. Seen it all and done it all. Okay.